so far in this course, we have considered functions from the complex numbers to the complex numbers, like this. But in this lecture, I will talk a little bit about what happens if you have a function of several variables. So we consider the space Cn consisting of all n tuples of complex numbers like this. And this is a vector space in a very natural way. And actually it's isomorphic to R2n as a real vector space. And you have a scalar product here. You can take the scalar product of two such n tuples just by summing zk times wk conjugate. And then, of course, this will also give you a norm of such a vector. You can say that the norm of z is just the scalar product of z with itself and then the square root of that. And so this you can use to measure distances in this vector space Cn. So the distance between two points z and w is just the norm of the difference. So this is a very natural vector space. And so what we'll do now is we consider functions from Cn to C, or more commonly perhaps from some subset, some open subset of this vector space. So this is very much like generalizing one variable calculus to several variable calculus. But as we'll see, there will be differences also. But anyway, the first thing that we'll define is what we should mean by an analytic function from Cn to C, or from some subset of Cn. So we make a definition. F from U to C, where U is a subset, an open subset of Cn, is called analytic if it is analytic in each variable separately. So this means that you have a function of all these n complex variables. And if you fix the value of all of them but one, say all these, and then you get a function of one complex variable. And that should be analytic then. And then you proceed, you can fix the values of Z1 and Z3, Z4, and so on, and just consider this to be a function of Z2. And that should also be analytic then. So if a function is analytic separately in each variable, then it's called analytic in this multivariable sense. Actually, in a course like this, it's convenient to add an assumption saying, for example, that F should be, say, class C1 or something. But it's a famous and rather difficult theorem by Hartog, which states that this assumption is really unnecessary. A function which is separately analytic in this sense will in fact be automatically of class C1, and in fact of class C infinity then. Okay, so when you do function theory for one complex variable, it's very common to study functions from the unit disk. You know, this is a set of Z complex number Z with absolute value less than 1. And just if you study functions from this set, then this will give you a good idea about analytic functions in any simply connected domain because of the Riemann mapping theorem. If you now study several variables, you can, if you like, in the corresponding way, consider the ball, say Bn, which is the set of all complex vectors like this, with the property that the norm is less than 1. So you can, if you consider this vector space to be a real vector space of dimension 2n, then this is just the ordinary unit ball. But as it turns out, very often this is not the most convenient set to study analytic functions of several variables. So for simplicity, in the following I will just let n be equal to 2. So we have 2 complex variables. And then we consider what's called a complex polydisk. This is the set of all complex complex vectors consisting of 2 complex variables then, with the property that both Z absolute and W absolute is less than 1. So this set is called a polydisk in 2 variables, and you can think of it as, well, in some sense it's similar to a ball, but on the other hand it's also similar to a square in a certain sense. So it's something in between. We'll have a closer look later on. A very large part of the theory, the one variable theory for analytic functions, is based on the Cauchy integral formula. So now when we go on to 2 variables in this case, the first thing that we should do is to generalize this formula to 2 variables. And this turns out to be rather easy then, and it's very natural to formulate it in terms of the polydisk. So let me write this theorem then. We suppose that we have a function, we call the variables Z1 and Z2 now, which is analytic in a neighborhood of, we take this standard polydisk then, and we suppose that it's analytic in a neighborhood of the closure of that polydisk. Then I claim that for every point in the polydisk, so Z1, Z2 lies in the polydisk, the open polydisk, then we can write f of Z1 and Z2 as an integral in the following sense. We have this factor 1 over 2 pi I, which we are very used to, but in this case it will be squared. And then we have an integral of f of zeta 1, zeta 2, and divided by zeta 1 minus z1 times zeta 2 minus z2, and then integrated with respect to these zeta variables. And what you integrate here over is the set where zeta 1 is absolute is equal to zeta 2 absolute is equal to 1. So this is really a part of the topological boundary of the polydisk. But the topological boundary of the polydisk is a 3-dimensional set, and this is just a 2-dimensional set. So it's really a small part of the boundary, and this is what is usually called the distinguished boundary of the polydisk. And you write it in this way. So this symbol is for boundary, and the knot here indicates that it's the distinguished boundary. Well, so how do you prove this? Well, fortunately, this is very easy to prove because it's just a repeated application of the ordinary Cauchy integral theorem. So if you just start with your function f of z1 and z2, then you can just keep, say, z1 fixed for the moment and consider it to be a function of z2, and then according to the ordinary Cauchy integral theorem, then this is equal to the integral over zeta 2 absolute equal to 1 of f of z1 zeta 2 divided by zeta 2 minus z2 d zeta 2 then. And once you have this, you can just repeat. Now we take this part in here, keep zeta 2 fixed for the moment, and use the Cauchy integral formula for the first variable. So then you have the following then. Let me write this factor here. And then now we have just this factor, which I rewrite in terms of the ordinary Cauchy integral formula as the integral over zeta 1 absolutely equal to 1 of, and then we get f of zeta 1 zeta 2 and divided by zeta 1 minus z1 and d zeta 1. And then after all, we have this integration with respect to zeta 2. And if you now just collect all the terms, put them together, you get exactly this formula. So this is the Cauchy integral formula in two variables. And you can use it very much for similar things as you do in one variable. For instance, it's almost immediate now that once you have this representation, you see that the function will be infinitely differentiable because you can simply differentiate under the integral sign here. And you also get actually an explicit formula for all the derivatives of this function. So if you take the derivative here now, let's write it as well. We take the derivative. We take the derivative j times with respect to z1 and k times with respect to z2 of f then by just differentiating this, and which means then that you differentiate what stands in the denominator, you get the formula that this is equal to jk factorial k factorial, and then divided by this factor 2 pi I squared. And then you have, again, this integral over, I write it as the distinguished boundary here now. And then you have f of zeta 1, zeta 2, and divided now by zeta 1 minus z1 to the power j plus 1 times zeta 2 minus z2 to the power k plus 1. And then also integrated with respect to these zeta variables. So this is very much like the formula in one variable then. You can also use Cauchy integral formula to derive the power series expansion in the polydisk. So to get the power series expansion, we essentially proceed as in one variable then. So we start with f of z1 and z2, and by the integral formula, then this can be written as follows then. And then we just rewrite this slightly by extracting the factor 1 over zeta 1 times zeta 2 in here. Then we get the following expression. 1 over zeta 1 times zeta 2. And f of zeta 1, zeta 2, and divided by 1 minus z1 divided by zeta 1 times 1 minus z2 divided by zeta 2 here now. And then we see that these factors here now, they can of course be expanded as geometric series. For example, if we take this factor here, then this is equal to the sum of, well, let's call it j, from 0 to infinity of z1 divided by zeta 1 to the power j. And similarly for the other factor down here, we can write it as sum over k then, of z2 divided by zeta 2 to the power k. And if you now simply insert these expressions instead of this part here now, what we get is the following. We'll get 1 over 2 pi I squared, and then we have the double integral, and then we have f of zeta 1 and 2 divided by zeta 1 times zeta 2. And then we have these power series here. Sum j goes from 0 to infinity of z1 divided by zeta 1 to the power j. And the similar term for the second variable. D zeta 1, D zeta 2. And then we can just, principally everything here is absolutely convergent in the here now. So you can move these summations outside here. And what you get is really then a double sum, which I just write by one summation symbol, but I write both j and k down here, going from 0 to infinity. And then you get certain coefficients that we call a, j, k, and then times the z1 part, which is here, z1 to the power j, and z2 to the power k. And the a, j, k here will be just then 1 over 2 pi I, well, squared times the double integral over the distinguished boundary of the polydisk then. And what you get is then up here f of zeta 1, zeta 2, and divided by zeta 1 to the power j plus 1 times zeta 2 to the power k plus 1, d zeta 1, d zeta 2. So you see here we get then a power series expansion for more or less an arbitrary, well, an arbitrary analytic function if it's just analytic in this polydisk then. And of course you can do this for every polydisk, if you like. So you have more or less the same kind of theory for power series expansions as you have in one variable, except that, of course, you have the series we have to sum over several indices here. So far, everything has been very similar to the one variable theory. So we have a Cauchy integral theorem, and we have power series expansions, and so on. So what I want to do in this last part of this lecture is to show you something which is completely different from the one variable theory. And to do that, let me start with the idea of analytic continuation. This is something that you can talk about both in one variable and in several variables. And one very simple way of formulating it is as follows. So suppose we have two sets here, two open sets, one contained in the other. So this small one is omega naught, and the big one is omega then. And then suppose that we have two functions f and g, which are analytic in omega then. And suppose that they agree on omega naught. Then the conclusion is that they will agree on omega too. So once you have, you know that these two functions agree on this smaller set, then it must also agree on the larger set. So for this to be true, you have to demand this set to be connected. But otherwise, it's quite a general fact then. So in particular, if you can extend a function from this smaller set to the bigger one, then this extension is unique. There cannot be at most one way of doing it. Now, if you consider the one variable situation, then of course, in general, there is no extension then. So if you have a set and want to extend it to a larger set, that can work for some functions, but it will never work for all functions. If you just take any set here and if you choose a function which has a pole in this point, then of course the restriction of that function to this set cannot be extended to the larger set, because it will run into this pole, so to speak. But this is very different now from the situation in several variables, or in our case in two variables. So let's consider the following example. We have the ball in C2 of radius 3. So this is set in C2 then, and it's all the points in C2 with distance less than 3 from the origin. And then inside here we have a smaller ball, which is B1. It's really the unit ball then, the set of all points with distance less than 1 to the origin. And then we can consider this set omega naught, which is B3 minus B1. So it's what's in the big ball, but not in the smaller ball here now. And then I claim now that if you have a function f, which is analytic in the two variable sense in omega naught here now, then f can be extended to a function which is actually analytic in all of the ball B3. So we let omega be equal to B3, and the statement here is then that given this function, there exists a function f which belongs to a set of analytic functions in omega, such that f is equal to, capital F is equal to f on omega naught. So it really says that we can extend the function from this set to this larger set in a unique way, of course. But the point is that this can be done for every analytic function in this set. So there's no way of constructing this kind of counterexample that you had in one variable. Well, how do you prove this? How do you prove that you can extend a function from this set to that set? Well, the idea is to use the polydisk again now. So the point is that if we consider this ball here, B1 and B3, then B1 is of course contained in B3, but we can also put the polydisk P22 in between here. So B1 is obviously contained in the polydisk P22 because if a point belongs to B1, then both coordinates must have absolute value less than 1, and here the condition is just that both variables has absolute value less than 2. On the other hand, this polydisk is now contained in B3 also, because the maximal distance to the origin from a point in the polydisk is that, well, the first coordinate can have maximal distance 2, and the second coordinate can also have maximal distance 2, and so the combined point here now can have at most they have maximal distance, which is the square root of 2 squared plus 2 squared, which is square root of 8, which is less than 3 then. So we have these inclusions now. And then we observe now, well, let me try to draw the polydisk here now. As I said, the polydisk somehow resembles a sphere, but also a square, and it's 4-dimensional, so I can't really draw a very nice picture of it, but I'll draw it as a cylinder here now, something like that it will look here now. That's what is supposed to be the polydisk P22, and that's B1. So the point is now that we can use the Cauchy integral formula, actually the one variable version, to define a function which is analytic in the whole polydisk and which will agree with the given function on an open subset of this omega naught here now. And then this integral formula will give you the unique extension to the whole set omega. So the point we define the function f, capital F of Z1, Z2 to be equal to 1 over 2 pi I times the integral of over W equal absolute value equal to 2 of f of Z1 W divided by W minus Z2 dW. So this is now an analytic function in the whole polydisk, simply because you can differentiate this expression under the integral sign now. You can differentiate with respect to Z1 because this is an analytic function, and you can differentiate with respect to Z2 because you have this simple factor in the denominator then. But what I claim now is that if we consider the set of points now where Z1 absolute is larger than 1, then f of Z1, Z2 will actually be equal to the capital F of Z1 and Z2 will be equal to the small f of Z1 and Z2. Why is that? Well, the reason is simply that if we have a point in the polydisk where this condition is satisfied, then you obviously are already outside this ball's B1. So this means that when you consider this integral here now, this function here will actually be analytic inside this circle here now for this fixed Z1. And therefore you can use the ordinary Cauchy integral theorem to deduce that this will be equal to f of Z1 and Z2. Okay, and the set of points in the polydisk where this condition is fulfilled is obviously an open subset. You can actually write it schematically something like this here now. In those parts, Z1 absolute will be larger than 1. And so then you see that these two functions will agree on this shaded set here now. And then the original function small f will give you an extension to the whole ball B3 outside the polydisk, and this formula then will give you an extension to the ball B1 inside the polydisk. So you have actually here now defined an extension to all of the set B3 or omega.